Produced by Avro Aircraft Limited at Malton, Ontario, the Avro car symbolizes the culmination of the second stage of an extensive program of research in the field of disc flight. Two identical vehicles were built for the purpose of conducting static tests, full-scale wind tunnel tests, and flight tests. Wind tunnel tests were performed at Ames Research Center, California, and static and flight testing was carried out at the Avro Test Facility near Toronto, Canada. For static testing, a rig was constructed to support the vehicle at varying heights above the ground. Strain gauge dynamometers at the three attachment points permitted lift and side forces to be measured throughout the program. Instrumentation, control, and fire extinguishing lines were installed from the vehicle to the adjacent control room. A remote fuel supply minimized the fire hazard. The first vehicle, completed in May 1959, was installed in the rig for an extensive series of static tests before being dispatched to Ames Research Center for wind tunnel testing. Initially, the vehicle was operated from the control room, where remote instrumentation recorded engine and turborotor performance, duct pressures and temperatures, and spoiler control positions, permitting comparison between theoretical and actual results. Static testing extended over a period of 5 months, during which time 32 hours of testing were performed without failure of any major component. Minor modifications proved desirable by analysis of early test data were introduced both into the test vehicle and into the second vehicle now nearing completion. Typical of these was the modification of the exhaust boxes to improve temperature distribution and introduction of a cascade beneath the turborotor to improve duct flow. The engine inlets were also modified to breathe from the upper skin in order to reduce high inlet temperatures experienced in early tests with the engines breathing from the internal ducts, and further tests were then performed. Introduction of these modifications enabled operation of all engines at full power. Tufting on the underside of the vehicle was used to provide visualization of the focus jet. Later in the program, the remote controls were replaced by the actual cockpit controls. It was now possible for the first time for the pilot to check performance and control characteristics with the vehicle in the flight configuration. Data obtained from oscillograph traces which recorded moment, lift, and center of pressure with variation of control position during static tests was punched onto IBM cards and fed into the IBM 650 computer. The output cards from the computer were then plotted to provide control characteristic curves. Using this data, control system problems were accurately simulated on the analog computer. The aircraft cockpit and pneumatic control system were reproduced using a compressed air supply in place of engine bleed air. The effect of control system modifications was also investigated before changes were made to the test vehicle. As testing of the first vehicle continued, manufacture of the second Avro car was completed. Preparation was made for the initial engine run, and for this test, the vehicle was secured by cables attached to each landing gear leg. This tie-down arrangement permitted checking of the engines at power settings in excess of the unstick setting, and also provided an opportunity for instrumentation and controls to be checked prior to tethered flight. Subsequently, the test was repeated with the vehicle raised on jacks in order to determine the effect of height on engine inlet temperatures, which were believed to increase due to recirculation of exhaust air. Tethered flying commenced with the vehicle restrained by 3 cables attached to the hoisting lugs and to anchor points in the concrete apron. During testing, the temperatures of critical items of equipment were recorded in the control room. Intercommunication between the pilot and the control room permitted monitoring of the tests by the flight test engineers. An alternative system of tethering, in which the vehicle was restrained by weight rather than by rigid anchor points, was then employed. Some difficulty was still experienced in controlling the vehicle, due partly to the influence of the tethers and partly to loss of lift with control application, which had also been experienced during static tests on the first vehicle. The control system was modified and the vehicle installed in the test rig with the upper nozzle closed except for 4 20-degree segments at the cardinal points. Tests were conducted with different central jet arrangements and various spoiler configurations. Meanwhile, after 32 hours of static testing, the first vehicle was being inspected and overhauled in preparation for the wind tunnel test program. Instrumentation specified for the program was also installed. Finally, the vehicle was crated in preparation for shipping from the Avro plant at Malton to Ames Research Center in California. Rig testing of the second vehicle continued, and the addition of extension links permitted the vehicle to be tested at different heights above the ground, and also allowed application of pitch during testing. These tests indicated some improvement in control characteristics, and the vehicle was returned to the tethers where static test results were confirmed, although the tethering cables continued to introduce random inputs, making accurate assessment of stability and control difficult. Sufficient data had, however, been recorded and analyzed to indicate that operation without the tethers was now possible. On November 12, the Avro car made its first free flight. In free flight, the vehicle showed a marked reduction of the oscillatory tendency experienced in the tethers. Control sense was correct, although more control power and less lag was obviously required. The number of control sectors was increased from 4 to 6, and after a further period of static testing, the vehicle was prepared for free flight in this configuration. With the increased control power provided by the 6-point system, the behavior of the vehicle was much improved. Stability within the ground cushion was better than before, and the gyro-stabilizing effect of the turborotor was now apparent. Although several satisfactory flights were made, it was realized that one characteristic of the spoiler control system in particular was compromising the performance of the aircraft to a greater extent than had been anticipated. Application of control reduced lift on one side of the aircraft with no corresponding increase on the opposite side. The ideal system would be one which would move the focal point of the jet without loss of lift. A system providing these characteristics had been designed and was being tested on the 1/20th scale model. A focusing control ring around the lower periphery of the vehicle replaced the spoiler control and deflected the jet to provide both control and forward thrust. Static test using steam provided flow visualization of focusing ring control operation both in free air and near the ground. Static and forward flight force tests were performed in the Avro wind tunnel, and flow visualization tests were also performed in the forward flight configuration. After successful completion of model tests, the system was installed in both vehicles. A further period of development in the static rig was required to check the characteristics of the new control system before flying continued. Most of the effort during this period was devoted to achieving a system in which the power required to operate the focusing control ring was compatible with the pneumatic power available from pilot and gyro stabilizer inputs. Tethered and free flights which followed were directed toward increasing the stability of the vehicle in the ground cushion and increasing the stable height of the ground cushion. Development of the new control system resulted in a marked improvement in attitude stability, control sense, and response rate. At a height of 3 feet and at forward speeds up to 20 knots, the vehicle no longer displayed the previous tendency to oscillate after pilot inputs, and short, stable flights with hands off were now possible. The height at which the ground cushion tends to become unstable, now known as the critical height, was found to occur at the point where the simple annular jet formed near the ground changes to the focus jet formed at increased height. Any change of attitude with the aircraft at this critical height causes the jet to become focused on the upgoing edge while remaining unfocused on the downgoing edge with resultant hysteresis. An additional, more powerful central jet was added to improve ground cushion stability. It was found, however, that an increase in ground cushion stability was accompanied by a decrease in control power, and the final configuration represented a compromise between the two requirements. Tests were also performed to establish the stabilizing effect of the gyro stabilizer, and it was determined that signals resulting from small changes of attitude were being lost due to system friction and control ring hinge moment. It was apparent at this point that some form of assist was required to transmit stabilizing signals from the gyro to the control ring, and design of a pneumatic booster was commenced. At Ames Research Center, the first vehicle was now ready for installation in the 40 by 80-foot subsonic tunnel. Here, tests would be performed to determine the transition trajectory from hovering both in the ground cushion and in free air. These tests were all performed using the focusing ring control system, which had resulted in the most successful free flights on the vehicle at the Avro test facility. The variable mount permitted testing to be carried out at heights up to 12 feet. Flight tests on the second vehicle were discontinued to permit introduction of the pneumatic control boost system. This involved the introduction of 6 sensing nozzles at the base of the central control shaft to monitor 6 pneumatic actuators mechanically connected to the control ring. The base of the shaft was now secured by a flexure, and only a small travel was required to transmit gyro-stabilizing signals to the actuators operating the control ring. Functional and frequency response tests were carried out with the pneumatic system pressurized from an external supply. A variable speed mechanical shaker was used to excite the control column, and measurements of control ring motion were made using potentiometers connected to a continuous trace recorder. Subsequently, the tests were repeated with engines operating and the system pressurized by engine bleed air. Tethered tests were performed to permit final checking of the power-boosted control system before free flying was resumed. Flights with the pneumatically boosted control system showed a marked improvement over the previous configuration. Stabilizing signals from the gyro were now quite apparent. The pilot reported that the feel of the aircraft was better with the new system, and that precise positioning without excessive effort was now possible. In summary, development of the vehicle resulted in a gradual improvement from the relatively unstable first flight requiring rapid pilot inputs through various applications of the spoiler control system, which was abandoned due to lift loss with control application, and ultimately to the introduction of the focusing control ring, which resulted in the most significant improvement to date. In the most recent configuration, with the addition of the pneumatic control boost, the vehicle displayed stable flight characteristics at a height of 3 feet and at speeds up to 30 knots. The wind tunnel test data showed, however, that the focusing ring control, though it had been developed for satisfactory hovering, was not good enough for forward flight, and that fairly extensive modifications were required to add an improved forward flight control system. Testing was therefore discontinued until the two vehicles could be modified in readiness for further wind tunnel and flight test programs.